So similar problem, we're trying to find the internal forces at A. We're going to follow the same procedure. We're going to do a free body diagram. And this time what we're going to do, I've drawn on the force, that's straightforward enough. We're going to have to find some reactions. So let's figure out what they should be. So it's pushing, so I'm going to have a reaction this way, that's going to be positive. Must have, so it's got it, this is for a built-in support, so that's what that's showing there. So it's going to stop it moving also in the y direction. So we're going to have something like that. And this time we do have a horizontal component. So this force here has a horizontal component. So we're also going to have a x component. Now I'm just going to draw it on the way it, I'll just draw it on the way it would actually be. So this is pushing this way. So this Fx must be this way. And what are we going to call these? Yep, so I'll call this, what will we call this? Call this point 0, point O, origin, whatever. And so this is going to be reaction O. So these are not internal forces, these are reactions. The internal forces are going to be at A. Better do that the same color though. So that's going to be RO, that's going to be MO, and that's going to be, that's ROY. This will be ROX. So that's what we're trying to find. We're trying to find the support reactions first. Now, when we're finding those support reactions, we should turn this line load into an equivalent point load. Okay, so the position of that point load's at the centroid on the x direction. Let's just put on our axes now while we're at it. So our x-axis is always going to be perpendicular to the beam. And our y-axis is going to be parallel to the beam through its center line usually. Y-axis this way. I need to start thinking while I'm talking. X, Y. So y-axis perpendicular to the beam. X-axis is parallel to the beam. Sorry about that. Now, yeah, when we're finding these reactions, we're going to turn this whole line load into an equivalent point load. And so the position is just the centroid, so this is just rectangular line load, so it's just going to be the center of the beam, 2 meters along, and the magnitude of that is just the area under that line load, so it's 10 times 4, 40 kilonewtons. I'm not going to draw this to scale anyway, so this is going to be 40 kilonewtons. I'm just doing all my applied loads in blue this time, so that there is 40 kilonewtons. Don't have any reactions at the other end because it's a cantilever beam. That looks pretty good. So what have we got? Everything? I think we have. So we've allowed for the line load, we've allowed for the point load. So what I'm going to do now is figure out all of those reactions. And after we've done that, I'll come back and we'll have a talk about trying to find those internal forces. Just quickly, I'll jump back in. What I'm doing here is I'm just finding the x and y components of this force, because basically you're splitting it up into the axial force and the shear force. And I'm also changing the point of application. Well, I'm not changing the point of application, but I'm changing the point on the arrow, which is showing the point of application. So this is showing the nose at that point. I'll just change it to the tail, just so I don't get it confused with this one. And then I'm just going to rub out the original force, because they're not going together. Those components are equivalent to that 20 kilonewton force at 30 degrees, and then I'm going to figure out what those are, and that'll just make it easier as we work through, because we already have our x and y components. Jump back in again. So I've got those components. What I'm doing now is just writing down the first equations. I'm going to have 3 equations to figure out these reactions. It's the same three equations we're going to use to find out the internal forces. So it's just the equations of equilibrium of a rigid body, which is the sum of the x components is 0, sum of the y components is 0, and sum of the moments is equal to 0. And so ROX, I've drawn it on the way I want it, so that's negative, so I make sure I put it in as negative, plus 17.32, and those are the only So this was the x component of this force, and those are the only x components that we have. So that's equal to 0, and then we've got the first component. Or the first reaction, sorry. Okay, I'll push on and get the others. So this has got all the reactions. So just for the moments, this one's positive, it's going anti-clockwise. You've got a moment from this force going clockwise, so it's negative, and a moment from this force as well going negative. What we could have done is combine these two into a resultant force, so 10 plus 40 would have been 50 kilonewtons. We could have done it that way as well. We've got the same answer. So that's just got all the reactions. So what I'll do now is we're trying to find the internal forces here. So I'll just redraw this with the two parts of that beam, and I'll put in the values for the reactions, and then we'll use the equilibrium on each side to try and figure out what the internal forces at A are. So what you'll see I've done here is I've split it where we want the internal forces, so that's the same as usual. But what I've done is I've gone back and I've put the UDL back. Why do I want the UDL back? Because I've got to allow for which part of the UDL is on this half and which part, sorry, yeah, it is a UDL, and which part of the UDL is on this half, or it's not a half, on this section. Okay, the right-hand side section and the left-hand side section. And so I've put, excuse me, I've put those back again. And so then I'm going to have to figure out the equivalent load for this again, and the equivalent load for this one here. And so I might just draw another diagram. You can do this in one step sort of thing, but you just have to remember when it comes to getting the internal forces, any line loads have to be converted back to line loads again, and then you calculate the equivalent point load for this side of the split and for the other side of the split. And sometimes if it's a triangular, I probably won't do an example of this, but suppose it was a triangular loading like so, and you've got a split here somewhere, you actually have to figure out what that value is. And so you've got to figure that out. You can just do it by scaling. Like if this is 0 meters, this is 4 meters, and that was one, let's say that's 3 meters. So the squares work, and that's 1 meter. This height is going to be 1/3 of the total height, just by similar triangles. So these two things are similar shapes. And so if the length is 1/3 of the larger one, then the height will also be 1/3 of the larger one. Or you could figure that out by, SOHCAHTOA, and then the ratio of these sides must be the same for both triangles either way. Okay, so in this case, it's just a rectangular line load. And so we don't have to figure out the value there. It's 10 kilonewtons per meter is the magnitude of that line load the whole way along. But we do have to turn it back into a line load and then figure out the equivalent point load for each half of the beam. So just be careful with that. And so I'll copy this, do it again, and put the point loads in after that. I'll leave this here. You wouldn't have to draw two separate sketches for each in your calcs, but I'll do it here just so it's clear for anyone who's trying to follow the working. So I think that's everything we need to do the rest of this problem now. Let me go back and grab these, because that's what we need next. So now we split it. Why are we splitting it? So we can see the internal forces. Split it, wouldn't be able to see them. I'll put it maybe down here for now, put this up. Okay, so that's it, split at A. This here is the point A, so is that. And we're going to try and find these internal forces. So we draw on the forces that we've revealed first. They were a bit like external forces now because we split it and opened it up. But we figure out the direction we want to put those in, need to make sure that these axial shear and bending, well, the axial force, shear force and the bending moment are all going to be positive. Okay, so to get positive bending, we're going to need a moment here, and we're on the right hand side, so it's going to be positive. So we're going to put a moment like that. Yeah, this is going to be interesting this time. Okay, so the next one, let me just move that A out the way a little bit. Then we want to have a shear force, this is usually called, so we'll call this MA. Do it the same color, MA. Then we're going to need with an axial force now. Do we have any axial forces here? We do, because of that. Yeah, that's cool. We've got an axial force here. And so we're going to make sure that that's in the positive direction for axial force. And so it's going on we are on the right hand side. The right hand side, it's going right. It's going to try and make a tension. So we're going to make it go that way. And what else? We need our shear force. We are on the right hand side. Right hand side down is positive for shear force. So right hand side down, like so. And you'd usually call this T, usually N, isn't it? Because you don't know whether it's tension or not yet. So that would be NA for axial force or normal force. That's where the N comes from, axial force or normal force. And the shear force, VA. Coolio. Okay, so now we're up to the stage of finding these. So we're switching back to the normal axes and the normal positives and negatives, not the internal force positives and negatives, because we're treating these like external forces at the moment. Because we put them on the right way around to get positives, if any of these comes out negatives, it means that the internal force will be negative. Whatever we put on must have been actually the other way around. So we put on tension. If we get a negative out, that means in fact it's compression. So this will be a negative value. And so this would be the right sign. That's why we're doing that. So I'll work through those calcs and see you on the other side. Oh, sorry. So what I'm doing is I'm just using those three equations of equilibrium for rigid bodies again. Sum of all the x components must be 0, sum of all the y components must be 0, and sum of the moments must also be 0. And I'll stop again if there's anything else I need to say. So this time, what we've ended up with, so I'm putting all these values in, I'm just being careful with positive or negative with respect to axes as we do it if we're just finding the reaction forces. I'm not thinking about positive and negative in terms of bending moments. I might just have to go and grab that again just while we go through this. I've explained it enough times, I reckon. So what we've found out now is the normal force 17.3, and it's come out positive, so that means this was right. And so therefore the tension, the axial force is positive 17.3 kilonewtons. So that would be tension. The shear force also came out positive, so it was also in the right direction. And for shear, positive on the right or negative on the right hand side, positive on the left, that means it's a positive shear force, and that's what we're getting. So shear force is also equal to 40 kilonewtons is what the shear force is. And then for the moment, this time it's come out negative. So that means this is the wrong way around. And so what should really be on that side is like so. And for the right-hand side, that's what it would be if it was all, that would be a hogging. It would be a hogging, so right-hand side is clockwise, and that's a negative bending moment, and that's come out as negative, so that's correct. So bending moment is equal to, you could say 55 kilonewton meters. And what could you do? So here you could put in brackets tension And you could put in brackets here, hogging. Or what you could do is you could rewrite it, and you could say, well, it's this one you're not really rewriting it. Well, you are. You're rewriting it, but you're not changing anything. So that'd be 7.3 kilonewtons in tension. And this would be, you could change, you say this is, well, it's 55 kilonewton meters, sorry, 55 kilonewton meters hogging, okay, without the brackets. Either way around would be okay, but we'll just keep it like it is, just do it like that, using the normal sign conventions. But the question might ask you, is it in tension or is it in compression? So you'd know, because this has come out positive, it must be in tension. Was it a hogging moment or a sagging moment? You could say, well, this must be a hogging moment because it's negative. Sagging moments are positive. So that's us done, but what we should do is just recheck that to using the other side if you've got time. So recheck it with the other side. Oh, I'm going grey too early. Story of my life. And so we've done that. So what I'll do is I'll do a quick check using the other side and make sure we get the same answer. Okay, so it shouldn't matter which side you use. And sometimes if you're short of time, you might choose the side to make it easiest to answer. So it might be easier taking one, might be easier taking one side than the other. But I'll just go through the check and we'll see that we get the right answer, or the same answer. I should just say on this side, so again, we're thinking of all those positive definitions. So that's positive for shear, that's positive for bending, that's positive. So just a reminder, that's correct, that's going that way, that's going that way. This time we're on the other end of the section, so we're using these are going to be the positive, these ones here, because we're on this side now. Check those, and we're getting the same answers for them all, so we can be fairly sure we've got it right, unless we made a mistake very early on. Cool, done. Next.